Now, Horst Knoerrer will be talking about symmetry breaking. So this is more on the quantum field theory side of things.
Well, thank you, and thank you for inviting me to speak. T.Balaban, J.Feldman, E.Trubowitz, and I are pursuing a long-term project, and the long-term project is to establish symmetry breaking in a gas of weakly interacting gas of bosons on a three-dimensional lattice. And the aim of in this talk, I want to, on the one hand, report about the status of this project, which is not finished, and on the other hand, I want to focus on a particular, maybe slightly more technical aspect of the program, namely the way the block spin transformations Antti has been talking about and are implemented together with the so-called background fields which arise when you do the functional integrals which arise in this context using the method of stationary phase. So this is the idea of the thing. First of all, let me describe the model, and we want to basically start from first principles of quantum statistical mechanics. So to describe a gas of bosons, we in the end want to describe it on C3, but we will approximate C3 by periodized discrete periodizations by discrete tori, and in the end we want to let this S go to infinity, so L is an integer bigger than 1, and in the end we will let S go to infinity, and the point is we want to prove that the limits of the corresponding objects exist. Now such a system is described basically by two quantities. One is the single particle Hamiltonian, which just describes one boson in this lattice, and for simplicity, let me assume that it's just minus Laplacian, or more precisely, the periodization of minus Laplacian onto the discrete Laplacian onto this torus I've written down. And then we have a particle-particle interaction. So that is a real valued function, which I assume to be translation invariant, and the Fourier transform to be positive. That is describing the interaction. And then what in physics one is interested in is expectation values of operators, like in Vieri's talk. So you take on bosonic Fock space, and just to remind you, bosonic Fock space is a direct sum of one-dimensional spaces, and for each you have a one-dimensional space for each configuration which says on the side x1 in X there are 15 particles, on the side x2 there are 13 particles, and so on. So you have, like for every side, you have a number which gives you how many bosons sit there, and the direct sum of this algebraically is the bosonic Fock space, coming with the topology, blah, blah, blah. And so what you have to do is you take an operator, trace of e to the minus beta h minus mu n times the operator divided by the partition function trace of e to the minus beta to n. And so these objects for defining the expected value of an operator are beta is of course 1 over the temperature. Then the Hamiltonian consists of two pieces. One piece, which we consider as a free Hamiltonian, is just implementing the single particle operator. So these A dagger and A are creation and annihilation operators at a site X. A creation operator at a site X just says, is a map which says if you have 17 particles at a site, then it will be mapped to the space where you have 18 particles on this particular site and nothing else changes. And the annihilation operator is the corresponding lowering operator. And if you, in second quantization, if you implement these data, then you have the single particle Hamiltonian implemented by this H0, and the interaction is as a quadratic expression in creation annihilators written like that. And we want to look at small interactions, so we have a small but non-zero real coupling constant. Mu is a chemical potential, and n is a number operator. On the top line you see h minus mu n. N is just a number operator. If you have such a space as I just described, it just sums up the number of particles in this particular one-dimensional space. And mu is a parameter which we want to run freely, and then at the end the density of the system, which we want to be positive in a certain range, will depend on mu, and mu will be adjusted so that it gets this density. Yes?
Do you remember h of x and y?
H of x and y, so we had the single particle operator h, which I write as a kernel. And so it's minus Laplacian. I'm always thinking of minus Laplacian, but of course we could take more general h. Now, so that is the basic setup. And observe that the number operator commutes with h. So that's easy to see. So that there is sort of a particle number symmetry. What we are really interested in are correlation functions. A correlation function is an expected value of creation and a product of creation and annihilation operators. And these creation and annihilation operators are the so-called Matsubara operators. They are obtained from the ordinary creation and annihilation operators by putting in sort of an imaginary time evolution here. And the creation and annihilation, and so we really have a 3 plus 1 dimensional situation. We have 3 spatial parameters and 1 imaginary time temperature variable, tau. And for each such data and each configuration of create or annihilate, we have a correlation function. In principle, these correlation functions would have to have a number of daggers and not daggers in the indice in the notation, but that would just make it look bad. And the number symmetry I've been talking about clearly implies that if you look at these correlation functions, and you want to make a trace, if you have, for example, more creation annihilations operators than annihilation operators, the whole thing will have an upper triangular structure with 0 on the diagonal, and the trace will be 0. So if you look at the system as I've described it here, where we have finite temperature and a finite space on the lattice, the number operator commutes with that. Now, the expected result on symmetry breaking in this situation is that we look at the infinite volume temperature 0 correlation functions. So we want to take the limit as the periodization gets to the whole lattice, and the temperature goes to 0, then the first statement is that these limits exist and have properties, namely describe a number symmetry breaking phase transition and Bose-Einstein condensation. And this statement is that if mu is negative, in other words, if we are below, the expected statement is that if we are below a certain density, then these correlation functions exist, still have number symmetry. So if you have as many, for example, if you just have one creation operator, then the expected value is 0, and you have a localized phase that these things are exponentially decaying. Basically, that was already done by J.Feldman in the last millennium. On the other hand, if you are above a certain critical density, and we can only work with working with that mu is at least order lambda above, or some power of lambda above the critical situation, then the number symmetry is broken. So that means that if you just have one creation operator, then the expected value is non-zero and the correlations are not even integrable. And then there are Goldstone bosons, etc. This thing has to be taken with a grain of salt. The way we take the limit, or one sees the symmetry breaking, is what Bogoliubov suggests, is that we, in the construction, we put in an external field, a small external field, which in the end we let go to 0. When we do it in this situation, the limit will be 0. When we do that, the limit will be non-zero. So that is a technical way of saying that the symmetry is broken. Okay. Yeah? But?
In C1, 0x.
No.
So what is the question?
The question is, isn't there an A missing? So should it be an A of x times a dagger of x, or only an a dagger of x? And the point is, it could only be an a dagger of x. That you have that if you have just one operator which is just raised in one particle, then the expected value, of course, is 0 here. But here, the same thing is not 0 in the symmetry broken phase, and it is non-zero more precisely in the sense that I've just described, with taking a limit of a symmetry breaking external field going to 0. So this is a singular limit, of course. If you do this external field to finite dimension, take the limit of the external field first, and then do the other thing, then it will be 0, but the other way around it will not be 0. It's expected not to be 0.
It's like the E-sig model, then.
Yeah. And okay, and there are, okay, as I already said, the first situation, I mean, there was most of it was done by J.Feldman, and Martin Lohmann looked at it from the functional integral point of view. In the second picture is in some way in physics literature justified by the Bogoliubov ansatz. The Bogoliubov ansatz starts with a different Hamiltonian, a Hamiltonian where you basically already put in Bose-Einstein condensation and symmetry breaking. So you replace a creation and annihilation operator by at a point x by the expected condensate density plus another creation and annihilation operator like thing. And if you write out that Hamiltonian does not commute with the number operator anymore. And then in physics literature it was studied, and it was actually, there was mathematical rigor. It's a mathematical rigorous works in 3 dimensions by starting with work of Benfatto in 1994, who looked at it in the situation in perturbation theory. If you ask me what about dimension 2, then in our approach all hell breaks loose. But Alessandro Giuliani and his collaborators have studied that situation carefully, and if you have any questions about 2 dimensions and the status of 2 dimensions, you should ask Alessandro. Okay, so that is the physics question, and if you look in the physics book, that's immediately turned into a functional integral. And it's turned into a functional integral, and the appropriate thing seems to be to take coherent state functional integrals. So coherent states are a generating system for bosonic Fock space, and then you write out traces and all of that in that language. And formally, you get a representation of, and let me just concentrate on the partition function. I mean, carrying around all the other objects is, we won't get that far that it really matters. So let me concentrate on the partition function. So this was this trace e to the minus beta mu h minus mu n, and we want to understand that. And they write it as a functional integral over complex valued fields, and the star in my notation means complex conjugation of some action. And this action looks not too unsimilar to the action of the Ginzburg-Landau model Antti was talking about. There are a few important differences. First of all, as I said, the fields are complex valued, not real valued. Secondly, I wrote a var phi instead of a phi. And trying to stick to his notation, look what you have here. You have the interval between 0 and beta, so that's not a discrete space anymore. So that is supposed to be some, you're supposed to have a field for each temperature or imaginary time in 0 beta, periodic boundary conditions, and for each of these points of this discrete space, that's not, for definition, not hard, of course, x. And the action also looks similar to the action Antti wrote down. So there is a quartic term, the second term is a quartic term, and then there is also a quadratic term. The quadratic term has a differential operator in it, and then it's corrected by the chemical potential. However, the quadratic term has the Hamiltonian, the minus Laplacian in it, in the spatial variables, and delta 0 is a first order derivative in the time temperature variable. And the Laplacian is self-adjoint. But first order derivative is anti-self-adjoint. So that means if you look at the spectrum of it, you get imaginary numbers. And that means that this formal integral I've written down here is an oscillating integral. You have e to the I something. And that makes a difference. While Antti sort of in a aside remark that there is a well-defined Gaussian measure which you could follow, this is not true in the situation of these oscillating integrals. Actually, that was all. I mean, one tried to construct complex valued Gaussian measures, and Cameron in 1960s or so already pointed out that there are usually too many oscillations that one can even define a Gaussian measure. And we looked at it in our situation and sort of mimicked Cameron's argument that really it looks hopeless. There are too strong oscillations that we can bound anything by absolute values, and we have to take these oscillations into account. So what we did is to go on and make a rigorous argument. Is we basically discretized the interval between 0 and beta with finer and finer discretizations, looked at sort of the model you get when you replace this integral by that, and takes a limit as the fineness of the discretization goes to 0, and proved that this limit exists and represents the partition functions. So that is a piece of an ultraviolet analysis which we had to perform first, and the result is that you get a functional integral which is now well defined. Namely, we have an integral now over a discrete space which I call x minus. So the time variable, continuous time variable got real, and a lot of degrees of freedom have been already integrated out across the original space x where I was working before, and it's a functional integral over fields which are now called phi, and we still have sort of a Gaussian measure, and we have an action, a dominant part of an action plus an irrelevant term, and I comment about the plus O in a second. First of all, so x minus is there, and then we have to restrict the integral to not all fields, but fields which fulfill a so-called small field conditions, so that everything makes sense. And the action looks very much like what was to be expected. So it is basically the same thing as before. This differential operator with the non-self-adjoint term in it, a quartic term which looks very much like what I'd written before, and the chemical potential. And however, there is an error created in this ultraviolet analysis. So there is a error term which I call E minus and an important point of it. We write these fields, these are complex valued functional integrals. And so everything is a function of phi, and of course phi star, complex conjugate, is a function of phi. But the point is that these error terms and all the terms we consider can be obtained by taking a function of two independent complex valued field, evaluated when you set one to be equal to the complex conjugate of the other. So phi lower star means I have a field which has nothing to do with phi upper star, and we have a correction E minus of phi star and phi, which is a function of two fields, independent fields, which, however, when you you have to insert that, and that will be important later when we do sort of contour shifting and the complex that we need analytic functions and two things. So this error term is what Antti in his talk would have called a perturbative correction in the second sense he used it, and actually we can prove that this is, in this small field region, a convergent power series in this phi star and phi. And then there is a large field analysis, so there are things which contribute, and they are what we call non-perturbatively small. They are smaller than any power of any power of lambda. So they are extremely small, but they are there. But I don't want to go into the large field analysis. So that is the functional integral we are going to study. And so we have this representation, and what have we achieved? If you look at the situation, and if you assume that, for example, that phi is constant, which is then if you look at the action, this action will be of, so if I draw here absolute value of Sept, and here the action, it's called act minus, then it has not a single minimum, but it has two minima, and then you sort of think of Z as a complex variable. So if you think of it in the complex plane, it's what people usually call a Mexican hat or so, which is the picture which arises if you rotate the thing. And this is usually considered to be a signal for symmetry breaking. The problem is that, so I think I can write it out explicitly. That is the analytic form. And the point is, yes, it's a Mexican hat, but it's a relatively flat and underdeveloped Mexican hat. It's the radius and the depth is both of order 1. And starting from that, so that is basically the functional integral we would want to start with. And starting from that, we start the infrared analysis. And this infrared analysis consists of 2 steps. So we take to a block spin renormalization group flow, two block spin renormalization groups flows. One is with what we call parabolic scaling and integrates out a lot of fields and continues to create a deeper and deeper and better developed Mexican hat. And in a way, one can see this sufficiently deeply developed Mexican hat as a justification for the Bogoliubov ansatz. Once the Mexican hat is very deep, it's advisable and also only possible to not expand the fields around the origin. I mean, if you are in that situation and you really want to look at the minima, and you always expand things around the origin, this is stupid. So, but you want to go at the bottom of the well and study situations there. So we introduce radial and I should say polar variables and do a second analysis here. So the first step I've described here basically is completed in small field, is complete in small field. So we have not really, we have arguments that all the terms we ignore are large field, but are very small, but I mean these are, we haven't put it all together and summed it all up. The second step, I will comment on later how far we are. So, but I said that I would comment on these block spin transformations. So to describe these block spin transformation, let me go to the blackboard. And so these block spin transformation, to remind you, are like that. We start, we have our original space, x minus, then we divide it into blocks, and we have a functional integrals over fields of x minus. We take a variable for each, a new variable for each block, or let's say for each center of a block. We fix the values of the fields at each centers of the block, then only integrate over fields whose average on the particular configurations of fields whose average on this block is the given value for the center of the block, and then integrate out over the fields on the center of the block. That is the block spin transformation. I mean, really yes. And then we do it again and again and again, and in case in the partition function, ideally if you have just one point and a number. So, and I want to focus, as I said, I want to focus a little bit on that situation. And I want to describe to you the induction step of what we are doing. In this generality, it's true for the both.
Minus, it contains time also?
It contains time. It's 3 plus 1 dimensional. It's this.
So these are squares or rectangles or?
They will be rectangles, and they will have parabolic size, so that the length scale in the spatial direction is the square of the length scale in the time direction. In the parabolic region, in what I call the elliptic region, it will be generalized squares. Okay, so let me describe the situation. So we start with a space x minus, and let me call the fields in there, and the fields in there I called phi and say phi lower star. And after a certain number of renormalization group steps, we will arrive at a situation where we have a relatively coarse lattice already, or coarse torus already. So the points here are centers of blocks, of centers of blocks, of centers of blocks, etc. So this is contained in here. And then I want to describe step one further. So we will get to some space x plus, which will have even fewer points. And let me call the fields here psi and psi lower star, and the fields here theta and theta lower star. Okay, and then we work with fields. So we have the Hilbert spaces of fields, complex valued fields. Let me call that here H minus, H, and H plus. Now, block spin transformation means that we average over blocks. Averaging over blocks means that we get an averaging operation which associates to each configuration of values here the average over the block, and that is that. And it will be modified a little bit. So we have an average operation, here we have an average operation which I call M. Of course I should call it A, but I also have actions which also called A, and since I'm German speaking, let me call it M for Mittelwert. And here we have all the composition of all the block spin transformations we have done until now. Now the idea is, the idea is inductively we will have a functional integral representation on that space. So a functional integral is an integral over, all these Hilbert spaces are finite dimensional in this setup, and functional integral over H. There will be some formula, and I will describe the inductive assumption first. Once we have that, we insert that one. To implement that operation, this averaging procedure, in a way, we integrate. Say that we write 1 as the integral over H plus d mu theta star and theta, and by that I just mean the Lebesgue measure in theta, in the complex field theta, e to the minus b times theta star minus m psi star theta minus m psi. Yes, and b is chosen. So that's really 1. Otherwise, we keep track of.
The alpha stars mean you really do have conjugates.
The upper stars mean I do have conjugates. The lower stars means I put myself on an abstract level. Okay. So what the idea is, you have, the idea is we have the functional integral here, so that will be an integral over psi star psi. We put the formula, this 1 in this form. We interchange order of integration, apply Fabini's theorem, and then integrate out the psi star psi's. There's a little wrinkle that the M, the averaging operation, is not really, you would think of taking for M the characteristic function of a box, but we need smoothness in this construction, so we take an iterated convolution of this characteristic function of a box with itself. 5 or 6 times. Okay, so that is the idea of how to implement the block spin transformation. Okay, let me describe to you, now I want to describe to you the way this functional integral inductively should look like in sort of an abstract setting. And so the point will be, of course, we will have that z is equal to the integral d mu psi star psi.
So the constant b in this Gaussian block spin transform, does it have any?
I mean, I just put it in to have the integral to be 1. Otherwise, I could also take b equal 1 and then keep track of all the numbers which come out in the case of partition function. So it will be e to the minus some action at the current scale. So I don't have minuses anymore, plus an e at the error term at the current scale, plus again something non-perturbatively small. And now this action is a little bit special. So I want to write this action. So this E again could be a power series of 2 independent fields. And this action itself.
Excuse me, here psi star, the star is upper star. So
here
star is really conjugation.
Here star is really conjugation.
So you're integrating only over psi, not over psi and psi
Yeah.
star.
Oh yeah, thank you. So I'm yes.
In there or not?
In here too. So this means deep psi star wedge deep psi over 2 pi I. Thank you. So this action can be written as a function of 2 independent variables, and even worse. So we get it as taking we have a function of 4 fields, fields here and fields here, and we evaluate them when this phi or phi star, let me just write a bracket for it, is equal to something called the background, which we call the background field of psi star and psi. So what I'm saying here is that we construct or get a map back from H which maps fields psi star and psi to what we call the background field of psi star and psi. And these background fields, and I will comment on the more precisely, are basically the compositions of all the critical fields which we get each time when we do the functional integral using stationary phase. So we have this map back, and it will turn out, and that's important and dangerous and bad, that even if we insert for psi lower star the complex conjugate of psi, in general the background field evaluated there will be different from the complex conjugate of the background field of psi star psi. So in other words, these background fields mess up reality conditions. Okay, and okay, maybe I should. Yes. So this action is actually a function of, is obtained by a pretty explicit function of these 4 variables when we insert for each psi star psi the background field associated to it. And now, means this action has naturally splits up into 2 pieces, A of psi star psi, phi star phi. is a term which basically comes from the iterated Gaussian convolutions, and Q is a pretty harmless positive operator. And then plus, and means the important part, and that is only a function of phi star and phi. And this A of phi star and phi is what we could expect, phi star, and then in general alpha delta 0 plus Laplacian phi minus a renormalized chemical potential psi of phi star phi plus some quartic term. I don't want to go into it. So the point is, these background fields have a particular property that for fixed psi star and psi, phi star background is a critical point for the map that we take, if the map phi star phi to A of psi star psi phi star phi. So, I mean, one can write out the critical point equations. I don't want to do that. So that is, these background fields is, we have this function of 4 variables. You fix 2 of them, then you vary the other 2, and these are critical. Good. Okay. So, and the point is, now we have that. We have this inductive description. We want to go on. As I said, we put in 1 into that, then integrate out the psi fields, and get something new on that level. And to do that, I might go back to the slides. So to remind you, at the beginning, we had a functional integral on that level, on the space I started with. Now we have a, after a certain number of block spin transformations, we have this representation of the partition function, which I just described to you. So it's obtained from an action in 4 variables by inserting the background field there. And then we want to insert, as I said before, this representation of 1. And I'm sorry, I still have the mistake of theta star and theta. It should only be d mu theta. And what we get is, of course, if we put that in, we get an integral with this effective action, which is the sum of the 2 terms. One is the averaging term, and the other one is which we had before.
Sorry, again, at the first step, what is the background field?
At the first step, the background field isn't there. Or at the 0th step, the background field isn't there.
Okay, so you generate with this...
We generate it, and I will come to that later. We will see in a second. We generate these background fields. Now, if we take this functional integral, and we want to do, since we have oscillatory integrals, we want to do it by stationary phase. So what we do is we put in, we fix theta star and theta here, and want to look, since we want to do the psi integral first, and we look at critical points psi and psi star. And then these critical point equations are pretty simple, algebraically. The point is, you would expect the gradients of A and all of that in there, but since phi fulfills the background field equation, these terms cancel out, and it sort of algebraically simplifies a lot. That's one of the nice features of this Balaban stuff. It turns out in our situation, these background fields have a unique solution under appropriate small field conditions again. And again, they don't fulfill this reality conditions. And the block spin, the main result about block spin transformations is the following. So we had taken the critical fields, which is theta star and theta, maps to psi star critical. And we basically define our new background field as the composite of the two. So the phi check goes from here to here. And the averaging operation is just the composite of the averaging operations. And then the representation of that we get is a product of two terms. First, let me first talk about the second term. This is just obtained by inserting the critical field into the integral. And that is this A check term, and similarly, and we get E just as a critical point, and of course everything is a function of theta. And this quadratic form changes a little bit, but in a harmless way. And the other term is, okay, if you do a stationary phase argument, you have the value as a critical point times a fluctuation integral. So you make a change of variables from psi to psi critical plus delta psi. And then you get the fluctuation integrals, and you just take get the differences in the exponent. And then the point is, now you have to integrate over a domain. Originally the integral was just over psi. If you make this change of variables, the delta psi will not be complex conjugates of each other. So really what you integrate over is this domain, which fulfills of delta psi's, which fulfill this bizarre condition. So in one variable it would be like an integral over something over a shifted real line. Good. Once you have done that, there are once you have this theorem, which is more or less algebra, there are a number of challenges or problems. And it again turns out that this background field is critical for the action we have, or for the dominant part of the action we have.
And this background field is what you will have to integrate at the next step?
No, the background field we always basically keep. I mean, just like here, we have the background field. We take the critical field, we have to integrate over the critical field. The background field is a map going backwards, which still describes the Hamiltonian, that the Hamiltonian is in the script A in this action, and describes what the action looks like. The background field is a map. I mean, the background field is really, one should call it a background field map. It's a map from fields to fields. It's a map, in this case, from H to H minus. So it's a way of associating two fields on the coarse lattice, fields on the fine lattice.
And would it be fair to say then that it is the map which gives you the critical point of the entire action with the constraint on the current or the next scale, actually? Is it on the, it's on the
question is it fair, is it the critical point for the for the action on the next scale, and that statement is yes. However, so I mean, I think, I'm sorry, it's a conventional notation of saying it's a background field, but really it should be considered as a background field map. Okay, so the resulting changes are the one term, as I just said, is a functional integral over this region D, which is an analog of a shifted line in the complex plane, which is usual for oscillatory integrals. So the point is you want to shift that back to the real axis in normal stationary phase. You do a Cauchy argument. You say that the terms of the bound, you take a finite interval in there, take the terms on the boundary. These boundary terms should be negligible, and you move it back. That's what we do. In several variables, I would call it a Stokes theorem. And of course, one has to argue that the boundary terms you get are non-perturbatively small in the sense I've been talking about. And then you get an integral, an honest goodness functional integral over just delta psi, and that we do sort of by a standard it's simpler than most cases. It's a sort of a modification of a polymer expansion to do this integral and estimate the logarithm of the outcome so that we can put it into the exponent. Then, if we can do that, then we get the representation of that as the integral of e to the log f minus a check plus e check, e plus e. And of course, in the end, we want to have something which is like what we had in the induction hypothesis. Most of the terms of log f can be subsumed in the e and create a new error term. We have estimates and everything. But
Can you remind, so f is the result of the single scale.
f is as a result of this fluctuation, single scale fluctuation integral. Should be here in the last topic.
Is the fluctuation around the configuration at the center that will be integrated?
Yes, it's a configuration around this critical point.
So, not necessarily the critical point. So you will have at the center of the blocks, or you have whatever configuration.
Whatever configuration. I mean, it has nothing to do. It has to do with
the
the
critical.
Constraint.
It's a constraint of. It's a constraint given by the critical field. Okay, yeah. Now, so f is this integral. No, sorry, maybe I didn't understand.
It's the single scale integral of the fluctuation.
It's a single scale integral of the fluctuation.
That you compute by shifting.
Which we compute by shifting the contour, get up to a non-perturbatively small error, hopefully non-perturbatively small errors. We get an integral over something real, and then we can do it. As I said, the outcome of this integral this log f will have most of it terms which we can put into the error terms, but there will be also quadratic terms and quartic terms, and that means, of course, we have to renormalize. That remember the explicit a, which I had written down, contained the mu, contained the quartic term, contained that, and so what you do is you shift that into the quartic terms, into these terms, so you get a new exponent. You write it as basically something action plus an error term in this case as before, but with a changed mu and a changed lambda and a changed quartic interaction and a changed coefficient in front of delta zero. As an aside, it's not quite as simple, since you have quadratic terms which are coupled pairs of points. So you have something like psi of x, psi star of y, and you wanted to write it as psi star of x plus some rest. So you basically localize, write some psi of y as psi of x plus an integral over a gradient, and so that's what you always do.
So after you've renormalized, the coefficients in this important part of the action have changed slightly.
Right.
The background field will now be the constrained minimum of this new one. The errors are not.
Yes, so as David points out, then this phi check of before isn't a good phi check anymore. It will not be the critical point for the new effective action. So we have to look at we have to compare the thing we have constructed to the new one and say it's basically not so important. Good. Now, okay, and that's actually hard and a lot of work. We have to prove that these critical field equations have solutions, have a unique solution, and estimate them. And there are a bunch of operators implied, and that's about 100 pages worth of work in the parabolic system. In the elliptic system, it's even worse. Okay, so let me.
Sorry, wait, no, wasn't that last step a preliminary one? I think I missed. So what is this last step? Wasn't this?
Yeah, so this, sorry. I mean, this is a preliminary step. I should have, in the logical order, it has to come first.
The last, okay.
The last. It was. I just put it down because sort of in a big part of the work, just in sort of in the outline. I first assumed just that we said I have a solution, but to do that one has to work. Okay, so at the end, I mean we are. So let me report about the status. The status is that as we have finished the small field analysis of the parabolic region completely. We get what we expect. We get a deeply developed potential well, and and then we do what I just indicated before. We start with the elliptic flow, and then we go to the. I mean, the parabolic is natural because we have this delta 0 minus plus Laplacian. That is a parabolic operator. Then we go into the elliptic region, expand the fields around the bottom, a point on the bottom of the well in basically complexified polar coordinates, and then it turns out that the relevant operators get an elliptic nature, and we do a different scaling, different kinds of blocks and so on appropriate to that. And in there of the program we have described here, in the elliptic regime, we think we have everything about the operators and about the critical point equations we need. That is complete, unless there are surprises in the next step that we need more information. We are in the middle of renormalization, or I would rather say we are about 80%. We are in the middle of doing the fluctuation integral, or maybe I would say we are about 80% into the fluctuation integral, and we have not apart from an impressionistic view, seriously worked on the renormalization. We hope we will have for the beta function, which now should describe an asymptotic free model, that we will have some kind of upper triangular structure which makes it relatively easy to analyze, but I don't know. Because we need the outcome of the fluctuation integral, obviously. Okay, so that is the status of the program, and thank you for your attention.
How do you know that you said that you need that the wall is deep enough, but how do you know that 1 over lambda over 3 over 2 is deep enough? So in other words, would we not better to do before the last regime, understand how much must be dip this Mexican hat and then see if all the problem can work. Because of course, how can be sure that these two approaches you need will
That's the match.
almost 90% of probability will not mix. So right, because there are several all the cases I know, no people was able to mix the two things. So
Yes.
now you are it seems that you are proceeding blindly against the wall, and but
Okay, I think, yes, I agree that in the end, of course, we are proceeding blindly against the wall, but we have to sort of have a little, put in, for example, a little radar or so. What we do is sort of, we have an overlap between the two regions, so which we can, where we sort of do the kind of elliptic flow also at the end of the parabolic region, so that we can basically continue, that we may have to make sure that we can continue and that we are deep enough so that the analysis and the error terms are sufficiently small, so to be able to go on.
so you are sure by other reason than 1 over lambda over with 3 over 2 is enough. You know that.
No, we don't know that, we hope.
But even heuristic reasons.
When I think we just go on as long as we can. And I think in the end,
Dimensional reasons.
You
That's
are
why 3, 2 and not.
no, I mean, I think from Benfato we sort of have an idea of what it should be.
So it's 3 over 2.
Yeah, it should be fine, but
Should be
it's non-perturbatively it's not a proof.
Okay, but there is a non-perturbative idea why
Yeah.
that is the now. Okay. Please.
initially in this parabolic region. You are somehow ignoring the inverse, the hump in the middle there, and you are overpowering it by the
In the elliptic region.
fluctuation integrals, by the mass that you get from the constraints. That's how you're overpowering the hump in the middle.
You mean in the parabolic region or in,
Yes,
in the first
parabolic
step?
region.
No, we really completely get the hump.
But then you would have to.
You mean we get everything as analytic functions in basically this domain?
No, I understand you get the hump, but the hump that's a negative mass of the hump. That mass is still smaller than the mass you get from the constraints.
Yeah,
Otherwise, you wouldn't be able to do the
yes,
right.
right.
So basically, you are waiting for this hump to get big enough so that you can go to the bottom of the well and get.
And that's what
Right.
Yeri
That's
asked
what
about.
there is asking. Yeah. Okay, no more questions. Only technical discussions.
Oh, over there.
One, sorry. Yes.
I'm a little bit confused by the role played by the background field. And so you're saying, if I understand correctly, you're saying that the result of the RGT can be expressed in a rather nice way using that background field as well. And so am I correct?
Yes, that's correct. So the point, I just repeat what you said, that the result of the functional integrals and of the renormalization group is nicely, we think, nicely expressed in terms of these background fields, over which we have to work very hard to get precise control of what they look like. That's analysis.
Yeah, it's the composition of all of the little translations you have to make for each step, because normally in these weaker interacting models we don't translate, we just work at an approximate minimum. Okay. Yes.
Is there some kind of hierarchical study of this kind of model where you can see a bit the flow of the relevant parameters like mu and coupling or in a bit heuristic way?
I think not hierarchical, but I mean perturbative, of course, of Sept.
Because there's a region where it's not really perturbative and
Yeah.
but, there's no hierarchical.
I mean, we didn't, as Vieri would say, we are blindly driving against the wall without saying we first study a hierarchical model.
Yeah, I mean, just a naive question. I mean, is there any simple model of these functional integrals, not even hierarchical, just where you can see the symmetry breaking?
well, of
And because you're talking
yes, I mean d by dt, or I mean Ising model, or I mean there are models.
I
where-
mean in these oscillatory integrals, not in symmetry breaking in general. In this particular, so you have an infinite dimensional oscillatory integral. I would like to understand a simple model, not to be just overwhelmed by all this computation. Just
Well, I mean, we tried every now and then to make a simpler model, but the point is that physics punishes you, and what happens is when you try to isolate one feature, the stabilizing effects of other features hurt us. So in the end, we gave up looking for simpler models, which sort of make this particular make these simpler. The point is, of course, what one can say is you make the quartic interaction ultra local and this kind of stuff, but this doesn't give substantial simplifications.
No, but maybe rotators in 3 dimensions.
Yeah. No, that was done by Balaban, and that we know.
Not oscillatory.
no,
Not
I want an
oscillatory.
oscillatory integral.
He wants oscillatory things.
Not statistical.
We have the one vector model, we have all the stuff Balaban did, but that were always real fields.
Because after all, there is this Cameron, so somehow.
Yes.
Yes.
Speaking of oscillatory integrals, so what is your intuition behind the statement that large fields contribute very little?
Yes, that's an important point. The point is, maybe Pranab's question is, we have this action which is basically quadratic. We have, so for example, the quadratic and the quartic part of the action. And the question is, if you have real fields, then you can say if the field is large, then the action is large, and therefore it contributes little. Now we have complex valued fields, and that argument is not true anymore because I squared is -1. And so the point is, when we, for example, there are several mechanisms. For example, I was talking about the shifting. So we have this region, and so we have this regime which I called D, which is off the imaginary axis. And then we have to move it back to basically to the real axis. And so we have to be able to make the thing wide enough so that if you put in the quadratic form, the real part will be substantially bigger than the imaginary part, like x plus iy. When x is much bigger than y, then x plus iy squared will still have a big real part. So we always, there are several places where we throw away making large field contributions. We always have to look for a situation like that, the geometry of these stuff puts us into such a situation. So it's an absolutely non-trivial aspect. We haven't done it all. We've written something like, we have looked at each individual aspect of it and made an argument that such a mechanism happens, but we haven't put it all together with all the large field, small field compositions, all the corridors and blah, blah, blah. Not even in the parabolic regime. We first want to finish the small field analysis and see that in our blind way we get to the end before we make a blind detour. But we always want to make sure that there is a very good convincing argument that each individual term is small pointwise, but that it integrates up, it's only heuristic.
Let's defer any more questions to afterwards. And